In this second tutorial, we are going to understand the three possibilities of the ambiguous case of the law of sines. So let's flip over to this part of our notes. The ambiguous case comes into play when the information that I give you is not necessarily enough information to have only one triangle. Sometimes there will not even be a triangle, and sometimes there may be two triangles. You recall when I'm giving you three pieces of information, you recall from geometry that there are four main postulates and theorems to prove that you only have one triangle. There's the side, side, side. There's the side, angle, side. There's the angle, side, angle. And there's the angle, angle, side. If I give you any one of these four sets of information, there is only one triangle that will exist. The only combination of A's and S's that will not necessarily work is the one that actually spells out a bad word. If I give you an angle and two sides where one of the sides is opposite that angle, then this is not necessarily going to make a triangle, and this represents the ambiguous case. I'm going to explain it in three different scenarios because there are three different scenarios that could happen. When I know that I'm giving the ASS, when I'm given the ASS information, I always draw my picture like this. I will always just draw an acute angle just like this. I label the angle right here, and in this case, that angle is going to be angle dollar symbol. I always take the opposite side, which in this case is going to be a star, and I dot it in because this is really the star of the show. It depends on what this side is to see what type of scenario we have. So I'm not going to put in a solid line because I don't know how long it is, if it's going to be long enough yet. We'll get into that in a minute. And then the other side that I'm given, in this case, I'm going to put hashtag. I always put that right here. So my pound symbol, my number symbol, or my hashtag will go right here. I always draw this picture when it's the ambiguous case. And that just helps me because I have to sort of memorize it from this picture. So let's start off with the relatively simple scenario. Again, we have this fixed angle. Nothing's going to change this angle. We have this fixed side. Nothing is going to change that side. This ray can come and go however long it needs to be. It all depends on how long side star is. So let's start off with the pretty simple scenario. Let's say that side star is bigger than or equal to hashtag. Okay, now let's stop right here. Why am I using all of these weird symbols? I like to teach this in terms of weird symbols rather than putting an A and a B and a C in here because I don't want you to memorize it from the letters because the letters can always change. I want you to memorize this from position. So I'm just putting these nonsense symbols here so you can just remember the orientation of them and the position. So let's start off with our first scenario. Let's say that side star is already bigger than side hashtag. I've got this side right here, and that side I'm going to put it right there on the point right here. And let's see, first of all, let's prove that this is a side that's longer than side hashtag. So that side is longer than side hashtag. And I need to make a triangle if I can. So if I hinge that right here, there's no way for this side to come inside the triangle. So I need to hinge this outside of the triangle. And I think that'll do it right there. You can see that as long as it's right here on this vertex, right here, that this side has to come all the way out here to even make a triangle, and it will. It will make one triangle, and that's what happens in this scenario. We will have one triangle existing. So again, that's if side star, this side, is longer already than side hashtag. It needs to kick all the way out here, and it will make one triangle. So that's the first scenario, and that's a relatively simple scenario, I hope, to understand. I'm going to put this side back. So the next scenario we need to talk about is whether a triangle even exists or not. So we need to figure out, if this side just went straight down to this opposite ray, it would make a right triangle. If we went all the way down, the shortest this side can be would make a right triangle. If it's any shorter than that, then we wouldn't even make it, we wouldn't even have a triangle. And I've got this orange piece to show that. This side, if I put it right here at this vertex, which is fixed, it's not even long enough to make a triangle. So this side's length would be the situation where we don't even have a triangle. The question is, how long does this side even need to be? This red piece should be exactly the correct size. So the question is, how long is this red piece? Well, since this red piece just barely makes a triangle, and we know that it's a right triangle, then we can use our SOHCAHTOA idea to figure this out. I'm standing here at this angle that's given, and the sides in this case that I would have is side star, which is opposite, and side hashtag, which is hypotenuse, because it's a right triangle. So the opposite and the hypotenuse is the sine ratio. I would know that the sine of my dollar symbol is equal to the star divided by the hashtag. And if I'm still interested in what star is equal to, I can solve this proportion as I've done before and see that star would have to be equal to the hashtag times the sine of the dollar symbol. This is the key piece of information that we need to see just to see if a triangle even will exist. Now again, this is why I always draw the triangle or the angle to look like this when I'm given the ambiguous case, because then I just need to understand that it's whatever this number is times the sine of whatever this number is. It's this side times the sine of this angle, which is the minimum length that this side needs to be. And in this case, that would be the red symbol. So if we are something that's less than that, then we don't even have a triangle. And that's our second case. If the star is less than the hashtag times the sign of dollar symbol, this magic number, if we're less than that, then we don't even have a triangle. No triangle exists. That's kind of nice because then there wouldn't be work, but we still need to be able to prove why. So if we draw a picture like this side, star, has to at least be this number times the sine of this number just to even make a triangle. Okay, so the third case, let's get rid of this orange. Uh-oh. See if I can grab just the orange. There we go. So the third case is, what if we have a side that is long enough, but goes a little bit past. It's bigger than hashtag times the sign of dollar symbol, if it's bigger than that, but it's still less than that actual side that's hashtag. What would happen then? Well, again, if I fix this vertex right here, this point of the triangle, and allow this side to hinge either way, you can see that we could hinge inside and make this triangle, hinging inside and making this obtuse triangle, or since it's long enough, we could also hinge it outside and have it make this triangle, which would be an acute triangle in this case. Or it could hinge in, or it could hinge out, or in or out. We actually have a case where there could be two triangles. And this is the case where this blue side is something that is indeed bigger, longer, than that magic value that we just found that's right here in this bubble, but it's not longer than the original given side here. So that's our second, or that's our third case, and that's the case where we will have two triangles. So if star is in between the magic number, the hashtag sign of dollar symbol, and in between the longest side, it's less than that, but it's greater than the magic value. This is when we have two triangles that will exist. I guess I'm getting excited about this, so I'll put exclamation points for each one. So let's put some numbers into this and explore this with numbers. Let's look at our first example. Again, you don't need to do this every single time I give you information. You only need to do this when I give you the ASS ambiguous case. I'm given an angle and two sides. So that has a possibility of spelling out ASS, but what I need to understand is that because the two of those pieces have the same letter, that this will definitely spell out the ASS. So in this case, it's the ambiguous case. I draw an acute angle. I label the angle that I have here, and in this case, it's 52 degrees. I start to dot in the opposite side, which in this case is 800. I dot it in just shy of it because I don't know how long this is, if it's going to be long enough. And then the other side, which in this case is side B, I put along this top part. So that's how I always draw my picture. So now I see that this is indeed case 1 because 800 is already bigger than 775. There's no way that this side could come in here or come in here or come in here. It needs to be kicking all the way out here because it's even longer than the 775. So I'm going to draw it there. I'm going to extend this ray, and we see that we do indeed have one triangle. This side is the 800. Let's see what else we have. I know that since this is A, and that's angle A, this is B, so this must be angle B. And I imagine that we're talking about triangle ABC, so I'm going to put this as a C, and therefore we're missing side C. So now let's solve this triangle. I know that I've got the A ratio, so I can say that 800 divided by the sine of its angle is equal to, there's no way of figuring anything out about the C ratio yet because I don't have either of the numbers. So I'm forced to go to the B ratio. I'll start with the side, 775, and it'll be divided by the sine of angle B, and that's my unknown. So let's cross multiply here, and I'm going to start with the side with the variable. 800 times the sine of angle B will be equal to 775 times the sine of 52 degrees. I'm going to divide by my 800 to get rid of this number. And now I've got that the sine of angle B is equal to 775 sine of 52 degrees divided by 800. If I'm looking for angle B, I need to get rid of the sine. So therefore, it's going to be measure of angle B is going to be equal to the inverse sine of this opposite side. So we've got 775 sine of 52 degrees divided by 800. I'm going to be doing the inverse sine of this to figure out what this missing angle is. Be careful of your parentheses. There's a main set of parentheses and then an internal set of parentheses when you push this sign button, or you could just do it all in pieces. Oops, I should not have put an equal sign because this will be an approximate. And when you plug that into your calculator, for angle B, you get 49.764 degrees. 49.764 degrees. Once I have angle B, it's relatively simple to go find angle C because the measure of angle C is going to be 180 degrees. Take away my 52 degrees, take away my 49.764 degrees. I know that you're not supposed to use rounded answers in the middle of your work, but because of our significant digits and addition, actually subtraction here, we're fine. It's going to be fine. When we subtract that, we get for angle C 78.236. 78.236. So now all we're missing is side C. So let's go do side C. I'm going to continue to use the A ratio since those are nice numbers. I'm going to say that 800 is to sine of 52 degrees, as side C, which I don't know, is to the sine of its angle, which is 78.236. Now I'm putting a little dot, dot, dot. This is a symbol for me to know that I'm using the exact number. When I've stored this in the calculator, I need to use this exact number for that in my calculator. What I mean by that is, once I've figured out this from the calculator, this angle B, when I do this information, I don't actually type this number in. I do the previous answer. On your calculator, I would type in 180 minus 52 minus the previous answer, and I'd have this, which is running in my calculator as the exact. And maybe I even store this in my calculator using that store button, which is the little stow above the on button, and store that in perhaps as alpha C so that I'm using it for variable C. Or just when I need this, I call up second answer. So this is just a symbol for me to know that I'm using the exact number. Let's cross multiply here. I've got C times the sine of 52 degrees is equal to 800 times the sine of 78.236 degrees. Let's divide the sine of 52 degrees away. And I'm going to have C as approximately, type this into your calculator. Again, when you need this number, you should be using second answer or something that's already stored in on your calculator as the exact. And C is going to be 993.892. 993.892. And that's side C. Moving on to example number 2. This time I'm given, well, I'm still given an angle that's 52 degrees, but this time it's labeled B, so I'll put B here. That's 52 degrees. Oh, I should have said that this is the ambiguous case. I'm given an angle and two sides, and two of the letters are exactly the same, so that has to be ASS. So I'm going to dot in the side here, which is 550. Again, I just dotted in because I don't even know if it's long enough yet. 775 is my other side, and I always put it right there. Now we have the case where, oops, it's less than 775, but I wonder if it's even long enough. To figure out if it's even long enough, I take this number times the sine of this number. That's why I always orient the picture like this. 775 times the sine of 52 degrees. When I type that into the calculator, I get approximately 610 dot who really cares, because 610 is already bigger than this. 550 is not even big enough because it's less than our 610 dot blah 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 blah. So guess what? No triangle can exist. And that's really all the work that needs to be shown. We need to figure out what 775 times the sine, this number times the sine of this number, figure out what that is, and if this side is not even that long, then we can't even have a triangle. This side is going to try to get to it, but it's going to come short right there. Not a triangle. And finally, our third case, I'm not going to solve both of the triangles that exist here, but I'm going to prove to you why two triangles exist. Let's look. We've got an angle and two sides, so that could spell out ASS, and it definitely does because two of the letters are exactly the same. So I've got side C, angle C here, 52 degrees. I'm going to start to dot in 650, and the other side that's given I always put right up here. So now let's see, is this side going to be even long enough? Because 650 is less than 775. But because we just did that work in the last problem, 775 times the sine of 52 degrees, that's our magic number, it needs to be, or it is 610 dot something. right? 650 is long enough. So that means that 650 is going to be the 610 and then a little bit more. So therefore, we can hinge either way. We can hinge inside like this, or we can hinge outside like this. And there are going to be two triangles that can exist. So I say we draw these two triangles as separate triangles. Let's draw this obtuse triangle first. I'll just do that right here. And that missing side, or that third side, I'm going to color code as that thick brown one right there. So that's one of the two triangles, or it's this bigger obtuse triangle out here. So I'll put an or, and we've got this bigger obtuse triangle where we've hinged out to get to it. And again, I would like to color code and put that hinge side, that missing side right there. Okay, so let's label our stuff. We still know that this is angle C, of course. That's our 52 degrees. 52 degrees. We know that this is 775. That was given, so that's 775. And we know that this hinging side is either 800 this way inside, or 800, not 800, what am I doing? That's a previous problem, I'm sorry. 650 inside, or 650 outside. This is side C. That's why it's opposite angle C. The other side that was given is A, so this must be angle A here, or angle A here. And again, I imagine that we're talking about triangle ABC, so that must be angle B up there, which means that little b is the side down here, which has two different lengths, and we'd have to solve for both of them. And again, I'm not going to solve both of these at this point since I've already solved plenty of them, but we do need to understand the link between these two triangles, the obtuse one and the acute one. Because when you start to solve these, you're going to be using this C ratio, 650 divided by the sine of 52 degrees equals the A ratio, 775 divided by the sine of A. But if you're looking at that in this triangle, guess what? It's the same exact thing in this one. 650 divided by sine of 52 degrees equals 775 divided by the sine of A. It's the same exact setup. So the question is, which of these angles, the obtuse or the acute, is the calculator going to give you? Well, I'm telling you right now that the calculator will always give you the acute angle. It will always give you this angle. So the question is, how do we get to this angle? What's the relationship between these two angles? Because if the calculator is always going to give us the acute angle, therefore we can solve the rest of this triangle. How are we ever going to be able to solve this triangle? Well, understand that this angle here is this angle right here in this picture. And this angle here is this angle in this picture, which obviously is a different angle. But since this is the same side, whether it hinges inside or outside, this base angle of this isosceles triangle has to be the same as this base angle. And if these two are exactly the same, and we're talking about these two angles, well, this forms a linear pair, and therefore these angles are supplementary. And that's the link between these two triangles. You'll solve this triangle first because the calculator will give you the acute angle here. And then once you have this angle, you will subtract that from 180 degrees and you will have its supplement. Supplementary means that they add to 180 degrees. So this is the worst type of problem because you actually have double the work to figure it out to solve the triangles. Thanks for watching this, and we will practice this in class. Bye-bye.